Good morning. Today I would like to introduce a few information on the solutions in ocean science of Teledyne Marine. My name is Stefan Könnecke. I'm with Teledyne Marine and specifically with imaging, with the focus of deep water applications and deep water sonars. I would like to introduce a couple of our solutions for ocean science and specifically some case studies based on our products and solutions in that area. So as you can see, there are quite a couple of solutions available already in the field on this visualization. There are, of course, the different platforms which are used with sensors as well as instrumentations. There are also imaging solutions and in situ sensors being used, and that range from ADCPs down to imaging sonars, multi-beam sonars, as well as AUVs and gliders in other solutions. One of our fields of applications and products is really multi-beam sonars in general. This is a widely ranged use product for ocean science, but also in hydrography and oceanography in general. So our multi-beam sonars can be deployed on various platforms, and they are used for mapping and monitoring the ocean from the shoreline down to full ocean depth. They are in ocean science used to create base maps for all kinds of detailed regional and local studies. And they are, of course, used to derive geology information, morphology, geophysics, oceanography information, as well as backscatter analytics and water column imagery. Here's a case study from India, where we have National Institute of Oceanography in Goa conducting a survey in the Bengal Fen area, where there was a hypothesis that there were cold gas seeps actually, and that there were eventually also in shallow waters accumulation of gas hydrates and the adjacent fauna attached to that. So this was the hypothesis, and the goal of the mission was basically to go out there, first of all map the bathymetry of the area to get some morphology ideas, where is actually possible sites of gas seeps, and then using the water column imaging of the deep water sonar installed, that is the Hydro3 DS, and provide imagery and all around this area volumetric data on where there are seeps, gas seeps, and what is actually the location they are coming out of the seafloor. You see two snapshots from certain locations, and this is just a visualization, just an example of there are tons of data being collected and analyzed, and this is one example where how the gas seeps show up in the multi-beam imaging. Now, during the study and during the search, gas seeps have actually been found, and they have been. The researchers on board the Sonars vessel have been able to localize where the gas seeps are actually coming out of the ground, and based on the multi-beam imagery, then they were able to further ground truth this information and basically use sediment cores to extract gas hydrates, as well as to find proof of fauna that is very specific for these kind of gas-saturated waters, gas-saturated sediments. So this is one of the research based on our multi-beam sonars. Another example of deep-sea sonars and deployment is really our Parasound or sub-bottom profiler. This is quite a versatile tool that can be used for many applications. It is profiling the subsea floor, it's profiling the sediments, the upper sediments of the seafloor, and therefore it can be used on studies for sediment structures, as well as sediment history, as well as sediment faults, and even sediment bodies flowing down a certain slope. Further, it's also being deployed for studies on gas seeps and gas hydrates, but I will look into this in a minute. So it's quite an indispensable and versatile tool for quite variety of marine geology and geophysical studies and applications. Now here's one example that is from the Arctic Ocean, where multiple missions have been deployed in the Arctic waters with the surface research vessel. This was the Alfred Wegener Polarstern. The Alfred Wegener Institute have been doing studies here in the area using the sub-bottom profiler to profile really the surface sediment layers, and the goal for the profiling for the mission was really to find out about the history of the glacial developments in the area. How have the ice shields developed in the last 10-20,000 years? So, and different artifacts have been, the researchers have been able to detect those artifacts and have been able to pinpoint them, and also have been able to derive certain knowledge from the glacial history, such as that the ice shield, for instance, was as deep down as 500 meters from the water level. So this is one example how the sub-bottom profiler has been used in terms of sedimental studies. I mentioned gas seeps and studies on this particular field before. So one of the goals of these studies is to locate accumulation of gas hydrates, as well as to find out how much of climate active methane, for instance, is actually coming out of the ground and is adding on top to the climate change budget. So I showed before one example from the National Institute of Oceanography where multibeam has been deployed to locate very efficiently sites of gas seeps. Now this is a sub-bottom profiler being deployed. The multibeam has the big advantage that it actually, when the ship is moving, that is actually covering a wide swath and can detect the gas seeps on a wide area at the same time, so it's very efficient. But it would only work if the gas seeps we are looking for is active at the very one instance. Now there are gas seeps which are semi-active and are active on a regular basis and are active permanently, but also there are ones that are active very irregularly. So the sub-bottom profiler, using that for detecting and localization of gas seeps, has one big advantage, and that is we are not only able to actually work on the water column, and this is the image that you see on this side. Sorry. But you also get some details of the sub-bottom of the sediments at the same time. So you have some proof of seeps of gas free gas in the water column, as well as you can see already the structure within the sediments that would indicate free gas, that would indicate faults and other features which are really linked and adjacent to these gas seeps. A further example is this typical sediment structure that you see in the middle, where you have this so-called acoustic blanket. Basically, the sediment layers, they do go through all the way. However, due to the gas-saturated sediments, gas really being within the sediment, the acoustic energy of the sub-bottom profiler is consumed, and this creates these blankings. So it's a quite nice tool to identify the spots where there is free gas in the sediments. So having the water column imagery as well as having the sub-bottom imagery at the same time with the same profile helps a lot to locate sites, even sites that are not currently active during the survey itself. One of our most successful products in the range being deployed for ocean science is really our range of ADCPs, acoustic Doppler current profilers. So we have been developing our ADCPs really from the 1980s, from the first commercial off-the-shelf piston ADCP, then to the first phased array on the Ocean Survey, and now the 7th generation of the ADCP, which is our pinnacle ADCP. Always increasing the performance, always also decreasing the footprint in dimension as well as the footprint in terms of power consumption. So the reason for this, the performance increase and resolution increase is obvious, but the reason for decreasing the footprint is really our customers are able to deploy these sensors on platforms where it hasn't been able to deploy before. With the phased array, it was deployed on ocean-going vessels on a wide range for long-term service, for instance. With the Pinnacle, even being smaller and more powerful, it is now possible to deploy that also on moored platforms where there is less power and less space available. One nice example of a study with using our ADCPs is this one, where vessel-mounted ADCPs have been used to monitor over a very long time the ocean currents and the water mass movements in between the very south of South America as well the Antarctica. So this is an area where the circular currents around the Antarctica are coming through and they are very bundled. So the water masses can be monitored here, and the thesis is that monitoring this site, it's very efficient to actually counterproof the oceanographic models in general for this part of the world. This study has been carried out with our vessel-mounted ocean surveyor over 20 years, where transect have been done between South America and the Antarctica many times, resulting in a huge data set, again over 20 years, with track distances of 5 kilometers, ADCP data ranging down to 1,000 meters, and resolution accuracy in the range of 1 centimeter per second. So this is a data set not only very useful for the particular transect and application at a certain time, at a certain year, but because of the 20-year deployment, it is also possible to use that to further look into the development of actually the motion of the ocean water masses. So not just a snapshot in time, but actually looking at the development over time. Another very nice example of applications of ADCPs is really that they are now being deployed on moored platforms for very detailed in situ studies. So these moored platforms enable the scientists to study really details on a certain location. And this is of course possible because the ADCP instrument itself has been developed in a way that it is now more compact and even more powerful and higher resolution. Some of these moored solutions are able to carry multiple ADCPs at the same time with different direction as well as different frequencies and resolution. So for instance, locations where water masses are falling down or as well as uplooming can be studied in very detail. And that is very useful, again, to support the oceanographic current studies in general. Another example of a very useful tool for ocean science out of our Teledyne Marine product portfolio is the Rapidcast. The Rapidcast is an underway profiling system that can be used to create profiles while the vessel is on the way. So these profiles can be sound velocity profiles, it can be salinity, temperature, pressure profiles as well. And the nice thing about the Rapidcast is really this underway feature. Instead of the ship stopping for a cast that can take minutes or even hours, this can be done while the vessel is actually still moving and collecting other data as well. So EFM Geomar in Kiel, they have been basically testing the system and trying to use the system in combination with classical ways to collect profile data. So in a certain area there were mooring systems installed for profiling as well as the meteor. In this case, the research vessel Meteor has been used to actually stop and do in-station profiles as well. Now, the Rapidcast at the same time was used basically to fill the gaps between those in-station profiles. At the same time, it was also possible not only to fill the gaps, but also to provide far higher resolution, spatial resolution while doing the profiling. In this case, the Meteor was running at 10 knots, providing profile depths of up to 140 meters. And basically the feedback from Geomar with respect to their application was it was a really nice tool to fill the gaps in between the different existing profiles and the solutions they have. And actually they have been able to identify physical presence of internal waves in the high resolution data of the Rapidcast. Talking about profiling solution, one of the things that also my colleague Dan mentioned is the Apex deep floats. This is a solution from Teledyne Marine where multiple of these platforms are deployed with different sensors on board, and then they eventually sink down up to 6,000 meters. Then they float freely, and triggered by a time signal, they would come controlled way up again, and then floating upwards. And while floating upwards, doing a profile with the different sensors on board. Typically that would be again salinity and obviously pressure and temperature, but it could also be other sensors. Now, this whole circle is done multiple times. When they come up, they deliver the data via satellite communication, but they may also receive new control information to actually modify the mission they are on. And once they are up and have delivered, then they can sink down again and do the whole circle again. So these floats are deployed for many months, even for years, and can profile an area for a long, long time. These floats, the Apex deep floats, are actually deployed normally in multiples, in multiple numbers, and then the different profiles they collect, they are usually plotted over time in these kind of plots. Here we see temperature, salinity, and oxygen, or temperature and salinity, and then while they are free floating with the ocean currents, they basically map the situation of the physical oceanography in the whole area. On the left-hand side, we see an application that was a sampling in north of the Antarctic, where Jamstec of Japan was doing some sampling with multiple Apex deep floats and creating a nice data set of profiles here. On the right-hand side, we have NOC from the UK doing the same thing in the Atlantic. So as could be seen by the different case studies, there are so many different ways of applications of our products and solutions. And actually quite a few of our products have been derived and approved by the challenges that scientific applications are provided to us. So that is my presentation. Thank you very much.
Teledyne Marine. Everywhere you look.